All right, so good evening to our US folks and good morning to our folks from India. Welcome to session number 3 today, and we have 4 talks for theme number 4, part 1, which is on microgrid and active distribution systems. And we're going to switch the order a little bit up, and we're going to start with Rabia Khan from WSU. So Rabia, I'm going to turn it over to you.
Thank you.
And thank you, Rabia, for stepping in while we were waiting for her to connect.
No problem at all. So I'll share my screen. So I think, can you see my screen?
Yes, we can.
Okay. Hello, everyone. Thank you for attending the UISS student workshop. My name is Rabia Khan, and I am a student of Dr. Noel Schultz. And the topic of my presentation is on optimal power dispatch in DC microgrids for rural electrification. So the outline goes with a background and some motivation about the research we are going to conduct, some results and discussion, and then we will summarize our overall work. And I'll conclude with explaining about the future work that we do. So rural electrification is an important concern that needs to be addressed. According to the Vice President of World Bank in 2013, she said that access to energy is absolutely fundamental for everyone, and which is a struggle against poverty. International Energy Agency says, according to that, 13% of global population is suffering from energy poverty. And out of that 13%, 85% of those people reside in the remote rural regions. According to United Nations, the United Nations have developed sustainable development goals that aim to provide clean, affordable, reliable, and sustainable energy to everyone by 2030. And this is the Sustainable Development Goal 7. There are other goals as well. So we are going to address that, and giving a bit of background about rural electrification. The people who are residing in remote rural regions that don't have any access to electricity or other forms of energy, they rely on such resources which are harmful for both the environment as well as their health. These resources include kerosene, wood, candles, and animal dung. So renewable energy sources can be used and can be a good source to provide electricity to those areas because most of these regions have natural resources available in abundance. Besides that, these resources could be a good usage for reducing the carbon footprint. So the rural electrification will mitigate energy poverty, improve human development, and enhance the economic stability. So there are multiple possibilities of enhancing rural electrification. One is grid extension, other is using isolated systems and devices, and third one is to install have islanded microgrid systems. Each has its own pros and cons. The grid extension is a possibility, but it is really expensive because we'll have the installment of high infrastructure costs, and there will be large distribution losses, and might be the resources are also depleting as the coal and natural gas are being used. Besides that, in the past decade, it has been seen that the small scale isolated devices like solar lanterns and things are being used, or a standalone system is being installed. But in the past 2-3 years, or maybe 4 or 5, we have seen that islanded microgrid systems is a better as compared to the rest of the two, because it has scalability features, modularity features. It will have low cost of electricity and things like that. So we'll be using the islanded microgrid systems for electrification. Considering the motivation behind our project is we need to have a suitable microgrid architecture. We have to decide a suitable source of generation for those areas, and we have to consider which mode of distribution and utilization will be preferable. So according to the survey, the remote rural regions, specifically in Southeast Asia and Africa, have abundance of solar irradiance, which is in most of the areas higher than the average required, which is 5.5 kilowatt hour per meter square feet. So besides that, in the past 2 decades, even the semiconductor devices have been advanced a lot, and the power electronics have improved. the prices have reduced a lot for the panels as well as power electronic devices. Besides that they are environment friendly and reduce the greenhouse gas, etc. Additionally, we need to decide which mode of distribution and utilization will be preferable for those areas. DC and AC each has its own pros and cons, but as most of the distributed energy resources are DC, we will be considering solar PV as the source and batteries in addition to that for storing the electricity. And DC loads are developed recently in the market for specifically for the remote regions. And if we have just DC sources and DC loads, then we can avoid a lot of conversion losses that are caused because of conversion stages from AC to DC, DC to AC, and things like that. And it is comparatively easy as we do not have to consider full frequency stability and voltage, reactive. So now going to the technical side, we'll be considering centralized optimization-based optimal power flow and the optimal power dispatch. So OPF, or the optimal power flow, is a fundamental tool that is used for power system planning, operation, analysis, and even designing. So the power flow equations that are used for designing, and I will be explaining these equations later on, are non-linear in nature. So when we try to solve OPF problem, the thing is that the problem becomes non-convex. So we need to actually relax the problem or try to solve by relaxing them to the convex relaxed optimization problem. So we could get a fine solution or maybe a converged solution to that. So different techniques have been introduced in the literature, among which semi-definite programming and second-order conic programming are the most famous and mostly used. And we will be using second-order conic relaxation. And according to the papers as cited here, that is found to give an exact and optimal solution for DC microgrid systems. So DC microgrid architectures have been used and introduced, but they have been mainly considered for optimizing distribution losses in the system. And even the planning of DC microgrids considered the converter losses in the system, but it was mostly considered that converter losses to be constant. But if we see the operational behavior of a DC to DC converter, the operation is not a linear curve. The efficiency and losses depend on the loading of the converter, that how much load does a converter operates, or at which point of the curve does the converter operate. So the power electronic losses do not stay constant, they depend on the loading. So we will be including both distribution losses and converter losses and trying to optimally dispatch power at different resources. So the model we are considering in our system is a branch flow model, assuming we have a graph and have n number of nodes and e number of edges. The nodes and edges are kind of interchangeable with the buses and branches in the system, and we are assuming the graph G is to be connected. It can be radial or mesh system. Each edge or each branch I and J are connected to one another. So the DC system we have is, as it is a DC system, so we are assuming the distribution lines are also DC, which have only the resistance, so we don't have reactance. Similarly, the active power is only participating, so real power, apparent power is equal to real power, and we don't have reactive power. So all the attributes or the values that we are considering just have the magnitude, so we do not have angles in these values. So these are the basic equations. First three equations are the basic ones that are used to develop a model of a power system. And the branch flow model that has been introduced for DC microgrid systems is represented by equation 4 to 6. And we can see that equation 6 is a quadratic equation which calls the non-convexity, and it makes hard to solve the problem. So we'll be relaxing that problem using second order conic program. So this is our optimization problem. OPF1 is the one that we have proposed, and OPF2 is the one that has been introduced in the literature. So we are trying to minimize the total distribution losses in the system, and we are trying to maximize the efficiency of the converters. So the architecture of we will be considering multiple nanogrids in the system, assuming a nanogrid to be like ith nanogrid. Each nanogrid has its own index, considering I is a nanogrid. and having each nanogrid can operate independently as a source, and it has its own load, it has its own battery, and we assume at the moment that we have one converter inside the nanogrid that will be operating. So the power injected at each output bus of the nanoconverter is equal to summation of power flowing to the other buses or of other nanogrids, and this is the same one that have been used, but the thing is that we are going to change this equation. So these are the other equations that we will be considering for the batteries and its state of charge, and we will be performing some dynamic analysis as well. So we'll be considering state of charge at multiple time instants. And these are some limits, bounds, upper bounds and lower bounds on voltage, power generation, and state of charge. And this is OPF2 is the one that have been introduced in the literature. So we'll be comparing how can we improve the performance of the overall system by comparing with just distribution losses and how what we have proposed distribution losses and improving the converters efficiency in the system. So we are using SOCP relaxation by making this to be inequality constraint, and we are using two assumptions. First is that the voltage magnitude at each bus have same upper bounds. It doesn't mean that it has same, it just means that all have same upper bounds for in per unit value, but the real value, the actual value can be different for each bus, and it does for every system as well. And total losses in the system is non-zero, which is true because every system has some losses whenever power flows even from one source to the load in any direction. So this is how we are modeling the converter losses in the system. The efficiency of it's better to look at the curve. Maybe I don't have the curve probably, but it's better to see the curve of the DC to DC converter because its curve is like, and it's not a linear curve, it's a non-linear exponentially increasing curve. And we can use up to higher coefficients, but for our study, we are including up to 2 quadratic term, like I is equal to 2. So this is how the efficiency is being represented, and then we can calculate converter losses in this form. So this is the model of the nanogrid system, where each house has its own panel, its own converter, battery, and load. And we are just using the architecture, just the model like of the 14 bus system, which is IEEE test system, but we are not using its constraints or parameters, etc. We are just assuming a system that has our own design nanogrids to be operating here. So this is the framework that we have designed for loss estimation, where we have each panel has its generation PGI, each load has its PLI, a converter processing power P converter, and batteries taking power PVI. And the power flow or the current flow through the inductor impedance between two houses, the nanogrids, is Rij and conductance is Gij. We are considering distributed generation distributed storage architecture, which means both generation and storage are distributed at each house. It's completely can operate independently. Oh, this is the curve of efficiency curve for the converter. So we take the efficiency curve for the from a data sheet considering its parameters, and we use the rabbit extracting tool to get the parameters value coefficients for the curve fitting function, and then we use that to calculate the efficiencies of the converters, and then we use them. So these are the simulation results for the 14 bus system. We are just using the architecture 14 bus system. We are not using its the exact values of the generation and loads, etc. So considering OPF1 that we have proposed, we can see the power scheduled at buses. If we see are comparatively, if we compare these two, are less as compared to what are being proposed. Like less number of buses are participating in sharing power with others as compared to what have been proposed, done in the literature. Similarly, if we see the converters efficiencies, we can see that this is the OPF2 which was already in the literature. So more converters are operating, but comparatively at a lower efficiency as compared to only 2 conductors operating at but comparatively higher efficiency. Similarly, here we can see the efficiency if we take some time instant here, more number of converters are operating as compared to considering the time instant here. And if we calculate the overall average, the converters efficiency for our proposed system has improved much. And this is the number of converters comparison for both systems. So the one that we have proposed, where we are trying to maximize the efficiency. So the way they work is that less number of converters operate, but at a higher efficiency as compared to more number of converters operating but lower efficiency. These are the multiplier curves we use for PV and load. So this is the results for the algorithm that we have proposed, and these are the different converter efficiencies. And we can see that less number of converters operate as compared to the one that has been used in the literature. So they are operating at less efficiencies, but in our system we have higher efficiencies, but less number of converters operate. Similarly, if we take the average of the state of charge of the batteries, here the batteries are operating, but they have comparatively average less value as compared to the what we have for our proposed system. So this is the overall what we have done, and we have designed microgrid. We considered a microgrid system using branch flow modeling technique. We designed the converter losses, and we solved it OPF for both distribution losses and power electronic losses. We consider all three parameters like constant, linear, and quadratic converter losses in the system. And then we solve this problem for both radial as well as mesh network systems. In future, we plan to include the distributed optimization technique for the same optimal power dispatch, where we give each household and nanogrid has its own capability to control how they share the power with one another. And then we will do some analysis of distributed optimization with centralized optimization. And I would like to acknowledge for UISS for this and helping us with conducting this research. So thank you so much. And if you have any questions and suggestions, please let me know. Thank you.
Thanks, Robbie. I appreciate it. I was a little worried that you had 49 slides down there. So
sorry.
No, that's okay. I was like, wow, she's going to be very quick. So so you did a good job making it in the time I asked. So thank you very much. So are there any questions?
I am curious a little bit about the impact of inverter efficiencies given the particular shape of the curves. First, did you operate an experiment with different efficiency curves, and what impact on the result did it have?
So overall, we tried these different curves are actually at different voltage levels. Like here, maybe you can see that these are different voltage levels. So whenever we tried, the main goal was trying to improve the efficiency, like to improve basically the loading, trying the dispatching the power in such a way that the converter will operate at a higher efficiency. So in every case, we saw that the converters were like less number of converters were operating, but at a higher efficiency than what previously done.
The shape of these efficiency curves essentially is pushing you to operate at the highest power level closest to the nominal. There are inverters, at least the ones that we worked with when I was at Georgia Tech, which had slightly declining curves. So the maximum efficiency was not at the peak power, but at the fractional power. And that was interesting and somewhat surprising to us. Okay.
Yeah, maybe I can consider, I should consider that too.
It's interesting and I think good that you are experimenting with it, because it may have considerable impact on the results.
Yeah,
distribution losses alone are probably not sufficient.
Thank you, sir. Thank you.
Okay, we've got time for one or two more questions. Are there any other questions? For those of you that may have just joined, we started with talk number 2 first, after we had some technical difficulties. So that's why for those of you that came in, it is talk number 2 that we started first. So.
Yeah. Hello, Rabia. Can you hear me?
Yeah, go ahead, Sanjeev.
Yeah. So I just have one comment. So like Professor Meslow mentioned, so yes, that's inverters have slightly different nature of the efficiency curve. So they decline after they reach a knee point or like a maximum point. But this is a DC-DC inverters. They have a different characteristics compared to the inverters. So the DC-DC inverters have kind of stable once they reaches to the maximum. Either they have a stable or maybe slightly decrease in the efficiency, but not drastically. So
right. So
yeah,
maybe that could be the next idea too.
Yeah,
go ahead.
one question I have is that, so because you consider these DC-DC converters connected to the PV, right? But how do we always operate at a maximum when there is no PV power input?
So actually we consider for both PV and battery, like this converter is for both PV and battery. So when I consider the parameters, we have chosen in such a way that batteries are, like, I know batteries are expensive, but batteries are of higher rating that when PV is not there, they should be able to meet the load demand. And we have also assumed that the loads in rural areas, like remote rural areas, are not very high. Like we can design based on what the load requirements are. So this converter, even if PV is not there, battery will be there. So they have to optimize whoever is connected, or even both are connected, or even it is charging. Like, understand?
Oh, got it. Yeah, so maybe you can also consider in future studies like what could be the impact if you just pushing all the converters to operate at maximum. So it indirectly extract a lot of energy from the batteries if there is no PV. So that of course degrades the battery life cycles. So maybe if you want to run for like a longer duration, so the results would be different. So I think that will be interesting to see in future studies.
Okay, yeah, thank you. I think maybe also inverter idea should also be good. Thank you.
So Rabia, you mentioned the fact that you the load patterns of rural. Where do you get that information on the where do you find information about the rural loading and expectations?
So actually we got, I have not included the references. So I got them from the NREL website. The NREL has shared the load data for different regions probably around the globe. Like I found that for Africa, and I have the location saved. I can share the details with you also. So I got the Excel sheet with load pairing data with 15-minute time step, and I converted that with average to 1 hour time step, and then use that load demand.
Okay,
yeah, that's great. A good point. Thank you.
No, thank you. All right, so thanks, Rabia. We're asking each speaker to put their contact information in the chat, so if people have follow-up questions. Particularly, we are recording these and we'll have